Yeah. Avevo visto la tua risposta. Stanno vedendo le slide.
Good morning, everyone. So we are going to restart and we go back to Phenomenology with Marco Cirelli. The agenda of today is the talk, but it will be the last one of the session. Then Juliana Perillo will go through the, so we go to the detectors world, and we start with novel liquid. Juliana will have the second part of the morning and the first part of the afternoon. Then we move to statistics with Claude in the second half of the afternoon.
Okay, so thank you very much. So we are going to continue about models of dark matter, candidates for dark matter. So proposal from particle physics and from astrophysics to fulfill the role of dark matter. And then we're going to talk about indirect detection, which will be the last part. And, let's see if we have time for colliders. But before we go on discussing models of dark matter, I think I wanted to point out something. I think I wanted to point out something because there was a question towards the end yesterday. So we discussed the neutralino, and I wanted to just point out that WIMPs, neutralinos, supersymmetric dark matter, or dark matter TV scale, these are all different concepts. Okay, so WIMPs are not only neutralinos, and neutralinos are not everything which is in WIMPs. These are two different concepts. So something that I present sometimes is the following. So you have, as we said yesterday, the neutralino as one of the most dominant candidates in the past decades, and you have many more, and I'm not going to redo the same thing as yesterday, but just to show you that the neutralino is one possibility within a supersymmetric dark matter. There are other possibilities pointed out, proposed by supersymmetry, for instance, the right-handed neutrino. We haven't talked about that, but it's another possibility. The lightest particle of the supersymmetric sector is a good dark matter candidate. We focus on neutralinos, but there are other possibilities. So SoUP dark matter is a wider set. And even wider than that are WIMPs, so dark matter at the weak scale. Not necessarily neutralinos. WIMPs can be non-supersymmetric at all, right? So there are models of WIMPs which are not supersymmetric. Two things completely different. And actually, let me insist a little bit on this. So sometimes people say, okay, so WIMPs are dead and old-fashioned because the LHC has not discovered supersymmetry. This has nothing to do with, I mean, it's a false argument. So WIMPs as dark matter candidates are still interesting, very interesting, at least in my opinion, because of the WIMP miracle we discussed yesterday. So they are produced automatically in the right amount. And this has nothing to do with the fact that there is or not supersymmetry and that the LHC has discovered something or not. These are two different things. One is automatically producing them in the right amount, still valid, still a good argument, WIMP miracle. And the other is we expect to have some theory like supersymmetry, which spit out a dark matter candidate, which happens to be a WIMP. That's a completely different thing. If the second thing collapses, we still have the other one. Okay, then more generally, you can have dark matter at the TeV scale, not necessarily related to weak interactions. So that's an even wider set. For instance, I'm quoting here a Technicolor dark matter, which at some point was fashionable, or some models of Kaluza-Klein dark matter. And yet this is wider than just WIMPs. Take a TeV scale particle that doesn't have weak interactions, like Technicolor dark matter, then it's in this set and not in this set. And even more widely, you can think about particle dark matter, which is everything which you have from particle physics, including, for instance, sub-GeV dark matter, which is something we'll discuss in a minute. So why I stopped presenting this kind of classification apart from the question I had yesterday? Because there are candidates that doesn't fit anywhere, so it's difficult to find a position where to put them. For instance, take the gravitino, which is the supersymmetric partner of the graviton. So do I put it here because it's a supersymmetric dark matter, but it's also very light, so should I put it there or where? And the same thing for the axino, which is another candidate for dark matter that people have proposed. So there are so many that this classification to me is a bit too restrictive. So I stopped showing that in talks and lectures. But the thing which is important to me is to say that SUSY, WIMPs, and particle dark matter are completely unrelated. Not unrelated, but different concepts with the relation that I just mentioned. Okay? Okay, so let's move on and discuss something different. So, yesterday we saw an example of WIMPs, neutralinos indeed, which are an example of WIMPs, which comes from a big, an ambitious, say, theory beyond the standard model. So we have the standard model, we have a problem in the standard model, which is the hierarchy problem. We want to solve it. We introduce this whole circus of supersymmetry, and we get a dark matter candidate as an output, almost as a byproduct of the whole theory. You can actually do, there are many other theories that use this, such as, for instance, I mentioned Technicolor or Kaluza-Klein and so on. They want to solve the hierarchy problem or other big problems of the model and produce also dark matter candidate. You can also have the opposite philosophy and still produce good dark matter candidates. One such example, the most minimal you can think of, is the scalar singlet dark matter. So it's really the minimal possible idea for dark matter. The idea is, I take the standard model, I don't want to solve the big problems such as the hierarchy problem and so on, but I want just to explain dark matter in some way. So I do the minimal steps which are needed to explain dark matter. Those minimal steps are just adding one extra field, so one extra particle, which is, for simplicity, for extremal simplicity, a scalar singlet under all the forces of the standard model. So it doesn't interact with any of the gauge forces of the standard model. So this singlet S is going to play the role of dark matter. And I add on top of it, so I need some extra ingredients, I add on top of it a symmetry that is conserved for S that goes into minus S. And we'll see that that will have a role. Okay, so you see the point, right? So I'm just doing the minimal steps which are needed in order to produce, to obtain a dark matter candidate. This is the simplest possibility that I have. So the Lagrangian of the model is very simple. I have the Lagrangian of the standard model, of course. Then I have a kinetic term for S, a sort of mass term for S. Indeed, so someone was saying yesterday, when theorists don't know what is the mass, they just put an M here. Okay, here it is. So I don't know where this term comes from. It's a mass term, why not, for the standard, for the scalar S. And then I have the other couplings which are allowed by the symmetries of the theory, which are this coupling here for with the hits. So quadratic coupling of S to the hits with a certain coupling coefficient lambda HS, and the quartic coupling of S to itself with this coefficient lambda S. So this theory is particularly minimal because I have as parameters this parameter m, which we'll see in a minute is not exactly the mass, this coupling here and this coupling here. So this one is not particularly important because it's just focus is just governing how much S interacts with itself in these diagrams here. So as long as lambda S is small enough, this is not too much self-interacting, and so I can almost forget about this coupling here. So then I have, so you see that the actual only coupling of the standard model of the singlet S with the standard model is through this term here with the Higgs boson. There are no other interactions, particularly no gauge interactions, because this guy is a singlet under SU1, under SU2, SU3, SU2, and U1 of the standard model. Now, what happens in the standard model is that I have electroweak symmetry breaking, so the Higgs gets a VEV, V, and so what I will have in the end is that this term here, this term here, and this term here combine to create, after the electroweak symmetry breaking, the actual mass of the candidate M, which is this parameter here plus what comes out from the VEV of the Higgs in this term here. Okay, so after electroweak symmetry breaking, after Higgs gets a VEV, the mass term for S will be given by this combination here. So you see that roughly speaking, I have something which has mass of the order of more than the Higgs VEV, something of the order of 100 GeV or something like this. And so we are going back to the usual weak scale dark matter. And then these couplings with the standard model become both in this term here and in the cubic term here. And that's it. So I have built a theory of dark matter which provides a good candidate, which is electrically neutral, okay, because of course I don't have any interactions with the standard model, including electromagnetism, which is cold because of the fact that it's heavy, and so typically its momentum will be much smaller than the mass, which is field interacting, because indeed by definition it has no interactions with the forces of the standard model, and which is stable. Why is it stable? Because of the ingredient that I haven't used yet, which is this symmetry S going into minus S. I don't know if this is completely obvious to everyone why this symmetry implies the stability. Yes, well, just in one word, it's actually pretty simple. So this symmetry enforces the fact that there cannot be any term in the Lagrangian with just one power of S. Right? Because if I have a term with S and then other stuff, one power of S and then other stuff, then that term would not be invariant under S goes into minus S. So S changes sign and okay. And what is a term with one S and other stuff? Well, it's a term where S decays into other stuff, right? A decay term in the Lagrangian is a term where you have S plus S times standard model fields of many sorts. So, okay, imposing, this is obvious, but let's explicate it. A symmetry of S goes into minus S means enforced stability for S because of the fact that you cannot have any linear term in S in the Lagrangian. Okay? So then one can do the phenomenology of all this. One can produce it through thermal scattering of this kind of processes in the opposite direction. And you can do direct detection, indirect detection, and so on, as we'll see later. So I'm not going into the phenomenology of this, which is pretty rich, but let's say you see that, again, we have a candidate that comes out from a theory which is sort of philosophically opposite to the one of supersymmetry. Still sitting around here, so around the TeV scale. Okay, let's move on and move somewhere else. So we move to this, to sub-GeV dark matter. So some other range of this kind of place, unless there is some question or some comment. Okay, so sub-GeV dark matter. So here we are sort of below the range of what typically WIMPs are. So say we are below a few GeV or 1 GeV. There's something called the Lee-Weinberg bound that tells you that roughly, if you are below 2-3 GeV, I'm not going to that, but 2-3 GeV, you are not in the WIMP regime because you cannot produce WIMPs efficiently thanks to the thermal freeze-out that we discussed yesterday. So we are below it. So this kind of idea has been proposed not so long ago, quite surprisingly, so only about 20 years ago, in a sort of, in different ways. So one is this, so I think this is more or less the first time that people discuss this kind of idea in this paper here from about 20 years ago, where they say that dark matter can be a scalar particle, so lighter than a few GeV, and so below the Lee-Weinberg limit, which is the thing that I was discussing a minute ago concerning WIMPs, because these particles can be coupled to a new light force, a new light gauge boson. So the basic idea here is to say, okay, so I don't insist on weak interactions, but I include a new force that will give me something more different in terms of mass. So this is the first proposal, but later it became a bit spelled out a bit more clearly, say, in what is called WIMP-less dark matter. So this is again a whole sector of ideas that is also sometimes called the hidden sector dark matter or secluded dark matter. These are all words for more or less the same thing, at least in basic principles. So let's focus on this idea, WIMP-less dark matter, about 2008, 2009. So someone yesterday asked indeed this question, so can I do some sort of equivalent of the WIMP miracle for sub-GeV dark matter? And here is the answer. So yesterday I told you that in order to produce the right cosmological abundance, I need this quantity here, sigma V, to be the value that we know from, we found yesterday, so 3×10⁻26 centimeter cube per second. And we found out that if I plug in the numbers for weak interactions, so typically TeV scale and typically alpha weak here, I do get the value that I needed. Now, of course, you can immediately understand that this can work also if I introduce a new force, which has a coupling, a different coupling, so let's call it alpha x or gx, and mediated by a new mediator, so typical new scale, which is m, which is different from the TeV. It's absolutely obvious, right? So if I have a g which is smaller than the weak coupling, then m is also, then can be smaller, and that produces the same amount of sigma v that gives me the cosmological cross-section before. Okay? So this is why it's called WIMP-less. In this case, weak interactions do not enter. There's a new interaction, let's call it X, dark force, whatever, that has as a mediator or a typical scale a smaller m, and then gives me the same annihilation cross-section that I need from in cosmology. Okay. So I should point out well, before first of all, what does it mean? It means that the particles of dark matter are produced through the thermal freeze-out mechanism, exactly like discussed yesterday, but with these new interactions mediated by this boson phi. Okay, so exactly like yesterday, I have chi annihilating into something mediated by phi's and being reproduced, and then this freezes out, and I have the thermal cross-section, the thermal production. Exactly like yesterday, but with different values. So one comment, which is rather important for me, is that this is a cute idea. Of course, it's pretty obvious. You just have to keep in mind that it's a bit less compelling in the sense that in the standard model, we do know that weak interactions exist, right? And those applied blindly give me the right annihilation cross-section. Here, I'm just postulating that maybe a new interaction exists, which I don't know, with the right scale, and so I get the right cross-section. So it's a double, it's a leap of faith in two senses. While the weak interactions do exist, and so WIMPs are, in some sense, much more compelling than the WIMP-less candidates. But still. Okay, so in this scenario, I can get right abundance for sub-GeV dark matter, for instance, or any other value. There is another setup in which you get naturally or sort of naturally sub-GeV dark matter, and that is the so-called SIMP miracle, so yet another miracle. So here I'm talking about, this has been proposed almost exactly 10 years ago in a series of papers by Leonid Hochberg and collaborators. So here the idea is that I consider scalar dark matter, which for some reason has a relic abundance set up by these kind of processes, 3-2 processes, as you see here. So what sets the relic abundance, instead of being annihilation into two bodies, like we said, like we did yesterday, are these kind of annihilations, 3 bodies, 3 dark matter into 2 dark matter. A variation of this is called cannibal dark matter because there are 2 dark matter that eat another one in order to survive. Okay, so this is the process which is at play, and it fixes the relic abundance with a certain coupling that I call alpha effective. So as long as this alpha effective is large enough, so this happens efficiently, you can write down the Boltzmann equation, as we said yesterday, and find out a typical prediction for the mass of dark matter that realizes this setup here. What you find is that the mass of dark matter is determined by a sort of combination of parameters such as this one here, which naturally points out to about 100 MeV, as long as this is of order 1. So this is the coupling, larger, so of order 1, and these are constants because these are just cosmological constants. So what you get is 100 MeV. So typically sub-GeV dark matter particle. This is, for instance, realized in a dark QCD-like setup, meaning that these interactions here are related to a sort of SU2 dark, SU3 dark, which we call a dark QCD, which explains why the coupling is large enough, so about over the 1. Okay, so I'm throwing out ideas to say that there are setups in which you naturally get something which is sub-GeV. Another one, which is somewhat popular, is this one here, asymmetric dark matter. So let me discuss that in a minute, which points to few GeV dark matter. So not really sub-GeV, but let's say few GeV or something like this. So someone yesterday mentioned asymmetric dark matter, so it's a good moment to review how this mechanism works. So here the idea is that I take dark matter to be a particle chi, and I consider its production in the early universe in a completely different way as opposed to yesterday, to the thermal result. So it will be again a relic from the early universe, but in a completely different way. So let's suppose that I have a particle which is somewhat heavy, say a few GeV, maybe I should have put 5 here, which is stable like the one we discussed yesterday in an expanding universe, and which the difference with respect to yesterday is that now I start with an asymmetric abundance. So I have a little bit more of particles with respect to antiparticles. So yesterday, for WIMPs in general, I was considering symmetric abundances, as we said. Now I consider that for some reason that I don't know, I have a little bit more particles than antiparticles. And this is completely equivalent to what we have for baryonic matter. We know that protons are a bit more abundant than antiprotons. We don't know why, but we know that. So we assume that in the dark sector, the same thing happens as in the visible sector. So I can do the same plot as a similar plot as of yesterday. So this is again the comoving density, like yesterday, as a function of time, or if you want, the inverse of the temperature. So again, in the early universe, you had the mechanism of production and destruction in equilibrium, and so you create and destroy dark matter particles, as yesterday. As the universe expands and cools down, you have that the annihilations continue, but the reproduction of particles from the thermal bath does not work anymore. So you have that the densities go down. And then the difference with respect to yesterday is that at some point, the annihilations stop, not because the expansion is such that two particles don't find each other, They stop because the antiparticles, which are here, whose density is in pink here, run out, finish. Because there is a small asymmetry, which is given by this parameter here, taken to be the same as the baryonic one. And so at some point, you have too few antiparticles against which the particles in blue can annihilate. And so what happens is that you're left with a leftover abundance of particles. Okay? So that's another way to produce a correct, let's say, abundance of dark matter particles, simply by exhausting all the antiparticles, all the targets against which they annihilate. So here, if you do the computation, you find that omega x is given by this, is determined by this combination of parameters. So cosmological stuff, the entropy density and the critical density. So these are don't interest. The mass times the symmetry, the asymmetry eta zero, which is this parameter that I put here. So here the rate abundance is determined by eta zero and the mass, which is actually pretty obvious in the sense that if I have a large initial asymmetry, I will get a larger abundance of dark matter, and if I have a small initial asymmetry, I will have fewer particles that survive in the end. Okay. So here again, comment is, okay, but this is engineered by hand. So if I put appropriate values for eta zero and mx, I get the right abundance. If I put random values, I don't. Right? The thing which is, on the other hand, interesting is that if I put an asymmetry which is equivalent to the one of the standard model, so of the baryonic matter, which is this one here, and I put a mass of the order of a few GeV, then I get omega x of the order of 26%, what I did. So this says that if the dark matter has an asymmetry which is the same as the baryonic symmetry, then this mechanism points to a mass of the order of a few GeV. It's actually the same ratio between omega dark matter and omega matter, replaced as a function of the ratio between matter, the mass of the dark matter and the mass of the proton. Okay, so that was a lightning review of the possible ideas concerning sub-GeV dark matter. So my conclusion is that yes, so sub-GeV dark matter models are possible. There are several ideas that point to sub-GeV, say from 1 MeV to a few GeV, and those are listed here, some of them that we have discussed. They give a good dark matter candidate with all the properties in different realizations. My personal comment is, okay, so this is less compelling than WIMPs or thermal dark matter particles, because as I said a few times, there are no, I mean, there is more freedom in the parameters that you choose. So you can get a good candidate, but not necessarily compelled to select one of those. So we should certainly look for sub-GeV dark matter, because why not? Because you have to search everywhere. But the theoretical motivations are maybe a bit weaker in that sense. Okay, before we move away, tell me if you have any comment or objection. Okay. So we move and jump again a bit lower in mass to KeV dark matter. And here in particular, the dominant candidate that people discuss always are sterile neutrinos. So again, lightning review of sterile neutrinos. Sterile neutrinos are, as a candidate of dark matter, are both theoretically motivated on one side and also phenomenologically motivated. So let me tell you the two things. Theoretically motivated because they are the natural completion of the standard model, of the lepton sector of the standard model. So you may have other lectures on this later, but you know very well that you have the standard model. The right-handed part of the neutrinos is completely sterile under the forces of the standard model. If we add them, so the three right-handed states of the neutrinos, one of them can be the dark matter candidate. The others can hold mechanical for other reasons, such as doing the leptogenesis or whatever your phenomenological model does. So typically, the mass of these particles as candidates for dark matter has to be heavier than a few keV, because otherwise they're not cold enough. So they have to be rather heavy. Let's say keV is the typical range to be safe from that. And if I have such a candidate among these ones, that is a good dark matter candidate, as probably we'll say later. Okay, so it's as usual neutral because it has no connection, no interaction with the standard model. It's stable. Well, we'll see in a moment whether it's stable or not. It's feebly interacting, no connections with the interactions of the standard model, and cold because of its mass here. Now, the peculiarity of sterile neutrinos is that they can decay. So you can have a diagram, you can write down a diagram, or you have a process in which a sterile neutrino decays into an active neutrino here and a photon. You see how it works? So you have the sterile neutrino which can mix, and I think you will see this later, or maybe you have seen already yesterday. A sterile neutrino that mixes with an active neutrino here. This active neutrino with a very low probability, but it can undergo a loop with a double boson and a lepton. Think, for instance, of I don't know, an electron here. If this is an electron neutrino, and this emits a gamma on one side and the neutrino, an electron neutrino on the other side. So bottom line, you get that the sterile neutrino decays into a gamma and a neutrino. Since the two-body decay, the energy taken away by this and this is just half of the initial energy, so half of the mass of the sterile neutrino, right? So why is this interesting? Well, precisely because this is one of the phenomenological motivations for sterile neutrinos. So I'm saying that sterile neutrinos can decay, producing a photon that carries half of their initial energy, mass energy, plus also a neutrino. So this kind of photon has been maybe seen in some observations of galaxy clusters. So in the observation, in a couple of groups, about 10 years ago, indeed, this group and this group, by observing clusters of galaxies, this set or this set here, detected the presence of a line, which is somewhere hidden in these plots, with an energy, so a photon line with an energy of 3.55 keV. Also, these other ones do agree. In some of these clusters here, with a rather high significance of the order of 4 sigmas in both cases. So these are the measurements. It's very difficult for someone like me to point out the existence of a line here, but I have to trust the statistical analysis of these people, and they say that a line is present at this energy here. Maybe you can see it here. Here it's quite prominent. So the blue lines, the blue points are the astrophysical background, and the line, the excess, is detected here in the red points. Yeah.
Sorry, I think I didn't write it down yesterday. It keeps coming up. What exactly is alpha?
Which alpha?
It was on the previous slide, and also the previous slide as well.
This alpha here? Yeah. No, this is just an index to say the leptonic family.
Okay.
So this alpha can be electron or muon or tau.
So it's not the same alpha as in the cross section for the.
No, sorry, no.
What is that alpha representing?
This alpha here. Let's find an alpha. This alpha here.
Yeah.
So this alpha here is like the fine structure constant, alpha electromagnetic. If it's alpha electromagnetic, it will be 1/137. And it's typically denoted with alpha. Here I'm generalizing it to consider alpha effective for another force which has a coupling Gx. So that's another alpha.
Thank you.
Okay.
The last alpha, sorry.
No, there is another alpha.
Yeah, it's the one that's squared over m for talking about the cosmological abundance of dark matter.
Yeah.
you have the cross sections, annual cross section times speed equals alpha squared W over n squared.
Okay, that's still this one here, but it's the same, this one.
Yeah.
Okay, so this alpha is the equivalent of the fine structure constant, but for weak interactions. Okay, so when so the summary is that forget about the alpha in that decay diagram, which is just an index, a Greek index. But here alpha is always the fine structure constant, which is the coupling G squared divided by 4 pi. If the coupling is the electrical coupling, so the electric charge, then it's the usual fine structure constant. If it's the weak coupling, then I call it alpha weak. If it's a new force, I call it alpha x, and so on. Or if it's the strong coupling, I can call it alpha strong or alpha effective, like here, for this new force, alpha x. Maybe I should call this alpha x.
Thank you very much.
Okay, so now we're discussing instead this decay. So this decay is motivating, has been motivating the idea that sterile neutrinos could be a good candidate for dark matter. In the sense that maybe in these clusters here, we have seen the effect of the accumulated dark matter in terms of sterile neutrinos, which are decaying and producing this excess line. So for this to work, you find that the mass of the neutrino has to be 7.1 keV, quite clearly, because the line that we observed is at 3.55, and so, as I said, we need, that's half of the energy taken away by the photon, so the mass has to be 7.1 keV. And for the flux to be correct, you have that the decay half-life should be 10 to the 29 seconds. So this is okay, because as we said the first day, this is much larger than the age of the universe, so it's a very tiny decay rate. And this corresponds to a mixing angle, so the mixing that goes into here, of about a few 10 to the minus 11. So something very, very small. Okay? So sterile neutrinos are possibly a good candidate, motivated by theory, and theory in the sense that they complete the standard model, and motivated by phenomenology in the sense that they can explain this excess in those clusters. How do we produce them in the early universe? So we have discussed thermal freeze-out, we have discussed asymmetric dark matter today, and there is a third paradigmatic mechanism for production of dark matter, which is the so-called freeze-in, which applies in particular to sterile neutrinos. So let me do a sort of parenthesis and describe freeze-in, which is the third main mechanism of production of dark matter in the early universe. It applies to sterile neutrinos, but not only, also to other particles. So let's be more general and discuss freeze-in in general. So freeze-in is a sort of opposite of freeze-out, as you can easily imagine from the name, and it works in the following way. So let's look at the usual plot. So usually we have, this is the moving number density of these particles as a function of time or temperature, or inverse of temperature. And usually we have something that does like this. This is the freeze-out paradigm. Here we have something that does the opposite, so grows from zero. So basically the difference with respect to the previous cases is that I'm starting from a particle, chi, which is a dark matter, which has zero initial abundance in the thermal gas of the universe. So all the rest is more or less the same as I said yesterday, or yes, for the freeze-out. But the difference is that now I have zero of these particles in the thermal bath. Why is that? Well, I don't know, maybe because they were not produced in inflation or at the Big Bang, or there's been a washout of their density, and so their density is essentially zero. But anyway, we start with nothing. Then, if these particles have a rate of production which is very small, starting from the particles of the thermal bath, you can have that mechanisms of this sort, so particles of the thermal bath, states, think of an electron or something else, produces the particles of chi, or this kind of process, or this kind of process, in a very, very slow way, but steadily. Okay, so this lambda is small. I will quantify small in a minute. And so these processes occur very slowly as time goes by. So the density increases little by little as the universe expands. So the typical values for which lambda is for which this process works well are small, very small, of the order of 10 to the minus 12, roughly speaking. Different values do apply. So you produce little by little some of these particles, and so you populate the abundance of dark matter particles. Then, at some point, usual story, as the universe cools down and the energy disposal goes down, the energy disposal will be lower than the mass. I have taken the example of 100 GeV particle here. And so these kind of interactions have to stop because I have not enough energy in the thermal path to produce particles calm. And so what happens is that the density at that point stays constant and doesn't move anymore, exactly like yesterday. So here, the mechanism is the opposite as yesterday. I start producing something from zero, and then at some point I freeze. Given the difference of the mechanism, let's call it freeze in. I get to a point and then I freeze. So I do reproduce the thermal abundance, so the matter abundance in cosmology, with a process which is a sort of the opposite of the one of freeze out.
Could you repeat why it needs to be heavy, and especially was we not like a KV is like?
No, I need. So this is just an example.
Okay.
I mean, the mass determines the moment at which freezing occurs. So the moment at which this stops. I'm using I could have taken any mass here. Okay, so I take 100 GeV because I want to do the parallel with the freeze out that I discussed yesterday. But if these are sterile neutrinos, indeed I was going to mention that, if these are sterile neutrinos, this would be KV, and so the freeze out would happen a bit later.
And the standard model particle that goes to the sterile neutrinos could only be neutrinos or something else?
Well, it depends. So for the case of sterile neutrinos, the equivalent of these processes here are the oscillations of the active neutrinos into the sterile neutrinos. Okay, so the active neutrinos mix and create sterile neutrinos. So they populate in this way the abundance.
Because if it would be any other particle, we should have found it already at colliders, right? It can only be the.
Yes, yeah. So that by discovering is very, very small, right? So you can also think of models with other particles, but this coupling is so small that even colliders might not work. But the typical case is instead that active neutrinos mix and oscillate into sterile neutrinos, producing this abundance here. So here I'm being more general and I'm using any mass, but applied to sterile neutrino, this is what happens. So here the final abundance is determined by the parameter lambda, which determines the cross-section for the processes I just mentioned below. So again, this is something less compelling because you have something which you have to impose by hand. Lambda is small or very small, y, we don't know, it's just a fact of our models. But still, you can produce particles in the right abundance if your model is correctly engineered. Okay, so sterile neutrinos are a good candidate. They are neutral, cold, field interacting, and almost stable. No, actually, they're not stable, but they decay with a lifetime which is so much longer than the age of the universe that we don't care. So again, another dark matter candidate, another possibility. Yeah. Why couldn't we have them? Well, because typically the interactions, so let's say the assumption is you can have also the freeze out of sterile neutrino, let me think. No, because their coupling is so small that they wouldn't be in thermal equilibrium in the early universe. So you start with an abundance which is very small. Also due to the matter effects that suppresses their production initially. So I had to think about it, but I think since you start from the zero abundance, I mean, the thermal result works as long as you are at equilibrium with the same abundance for thermal bath particles and Cirelli neutrinos. But this is not the case for Cirelli neutrinos, given their small couple. I'll get back to you if I have a better, clearer answer. Yeah.
What mechanism can we use to search for this? Because I know that the short baseline anomaly recently is kind of ruled out.
Yeah, but these are very heavy. These are heavy particles, so these are the order of the keV. So in accelerators and so on, you usually look at the lighter ones, so maybe one of the other states, or not those that can be the dark matter. So here the search is essentially the cosmological one. So testing whether these signals are true or not, actual signals or not. So the story is that this signal is pretty old, as you see, from 2014, but it's still out there. There is no clear answer whether this is related to dark matter, neutrinos or not. It can be an atomic line. It can be some sort of the excitation of some atoms in those clusters, in the gas of those clusters, most notably potassium, which has a line which is close to this energy here, which is why people have discussed the fact that these are bananas and not neutrinos. Right? There are papers that say Cirelli neutrinos going bananas, in the sense that bananas have a lot of potassium, and so the experiment which was supposed to test this was a Hitomi, so a satellite which flew in 2000, forgot which year, a Japanese satellite that exploded a few days after launch, or a few weeks after launch, and so it hasn't been able to check the details of this emission here. Now, another satellite has been launched, which is called Astro H, I think, and I'm not sure that the results are conclusive yet or not. So the idea is let's go and check and get the better details of the signal in other systems as well, and see whether it's confirmed or not. Okay, so where was I? I was here. So let's jump again, and let's move to the very low mass, the ultralight fields. So in particular, axion and axion-like particles. Okay, so again, here you're going to have a full lecture later in the week, so I'll just give you the basics, which are the following. So I will motivate axions and axion-like particles in a couple of minutes. So axions are a candidate which is, again, theoretically motivated in the following way. So if I take the Lagrangian of the Standard Model, I can add to the Lagrangian of the Standard Model this term here, which is called the strong CP term written here. So now this G3 is the coupling of SU3. This is the field strength of the gluons. So as it is for the electromagnetism, but for the gluons, these are constants. And then you have a coefficient in front, which is the theta angle, the strong CP angle, which is in front here. So I'm saying that on top of the Standard Model, I can add such a piece because it's completely consistent with all the symmetries of the Standard Model. So it's allowed as a term in the Lagrangian. Actually, it's more than that. You must, as always in quantity theory and quantum mechanics, if the term is not forbidden by something, you must add it in some way, in some sense, in the sense that it will be otherwise generated by higher order corrections. So this term does exist in the Lagrangian, the full Lagrangian of the Standard Model. Now, this term, why is it a problem? It's a problem in the sense that this term induces a dipole, an electric dipole moment for the neutron, which is given by this expression here. So it doesn't matter why these are the parameters that enter, the mass of the pion, the mass of the neutron, the electric charge, times this theta angle here. So this term causes the neutron to have a small electric moment. What does it mean naively? It means that the neutron is a neutral particle, but essentially it has a small plus and a small minus ends, okay, in some sense, naive sense. This electric dipole moment of the neutron turns out to be 10 to the minus 16 theta e times centimeter. So if I plug in the numbers here, I get 10 to the minus 16 times theta. So the theory predicts this value for the electric dipole moment of the neutron. But the thing is that experimentally, if I measure it, I find that this is consistent with 0 and actually smaller than 3 × 10⁻26 e centimeter. Okay, so much smaller than the prediction from the theory. So the question is, why is it so small with respect to the prediction of the theory? So why theta has to be such a small value in order to be consistent with the theory? Theta smaller than 10⁻11 or so. One of the possibilities is that the value of theta is not a free parameter, so it's not cannot just take any value, but it's something which is dynamical, something which is driven to a certain value by some sort of dynamics, meaning that theta can be promoted to a field. And this is the idea that Peche and Quinn had in the late 70s or early 80s. Okay, so if theta is dynamical, so it's promoted to a field, this field can have a potential. Think of, for instance, a parabolic potential, which has a minimum close to 0 or in 0, and which is why the field, the value of theta is driven essentially to this value 0. Okay, so I'm reviewing very naively things which will take probably hours to explain, but let's say the basic point is the following. So I explained the smallness of theta, promoting it to a field, and assuming that there is a potential that is related to some symmetry, U1 of the J Queen, that drives theta to 0 or close to 0. Okay, so you see where the field goes. The field is the axion. So this field, which is responsible for this mechanism, is the axion, and it can be also a good dark matter candidate. So as you will probably see later in the week, if this is the phenomenon which is at play, then you have a sort of prediction for the mass of the axion, which is of the order of 0.5 millielectron volt, so a fraction of a millielectron volt, times a factor which is related to this f of a, which is the scale at which this symmetry here breaks. So this is typically 10 to 10 GeV, but it can be different, and so this value can change. So in the minimal setup, you have f of a equal 10 to the 10 or so, and so the mass of the axion is expected to be a fraction of a millielectron volt or something like this. Okay, so that was very quick, but also tells you that dark matter can be in the form of axions, which are neutral particles because they have no interactions with the standard model fields. They are stable, decay, they are field interacting, they have no interaction with the standard model fields, and they are cold not because their mass is larger, but because their production mechanism, I didn't discuss it, but the production mechanism is such that they are produced with a very, very small momentum. So that's the so-called misalignment mechanism, which we are not going to discuss here. But they can be cold. Okay? Yeah.
I thought that the city value internal would be generated by higher order correction. Could you explain better this?
It means that if you don't put it at tree level in the Lagrangian, something like this will come out from loops and from higher order corrections. Okay, so necessarily, since it is consistent with all the symmetries of the standard model, if you sort of forget it, it will come out naturally. You have no way to forbid it. I don't know if that answers your questions more or less. No.
Thanks.
Anyway, it has to be there. There is no way to remove it unless theta is equal to 0, but we have no reason to think that it is equal to 0. And so then we are left with this argument here. Yeah, okay, yeah.
Just to note that as soon as you mentioned the actions, Gianni Carugno appeared from the door. And Professor Carugno will cover this topic tomorrow morning on the phenomenological and also on the experimental side. So just to give you the link tomorrow.
Okay, so I hope nothing of this is wrong, and he will otherwise correct it. Okay, so let's jump to the last candidate that I want to discuss, and here we go all the way to the other end of the spectrum, which are primordial black holes. Yeah.
Maybe before we go away from ultralight particles, so you mentioned just scalars that got produced by misalignment, but I think I read somewhere that there's a possibility for ultralight vector particles. This is like a serious thing, and is there also like a production mechanism for this?
Certainly yes, but I'm not.
Okay, so if anything, it's really a small part of the community working on this. It's not a well-known thing of ultralight vectors.
I have nothing specific in mind, but yes, equivalent of dark photons can also be very light. I'm not completely sure. Okay, so let's move to astrophysics essentially, and let's move to primordial black holes. So what are primordial black holes? The idea is that, one way of introducing primordial black holes is a sort of, as dark matter candidates, is sort of go back to the basics and think that we are back in the 80s, say, of the last century, and ask ourselves what dark matter could be. Okay, so at that time, we learned, say, at school, that dark matter could not be something related to astrophysical weird objects. I'm just throwing out ideas. So dark matter cannot be, of course, a gas or ordinary particles, because otherwise we would have seen it, for instance, in those cluster collisions and so on. But people were thinking, okay, so dark matter might be, so this missing mass in the galaxies and in clusters can be in the form of black holes or brown dwarfs or, say, dark astrophysical objects which are not emitting the light, and so that's why we don't see it. So a population of small black holes going around, or dense stars such as brown dwarfs. So people looked for them using a strong lensing, using surveys of strong lensing, which essentially means that, as yesterday, but now in the strong regime, for the lensing, you look at distant stars, for instance, in the Large Magellanic Cloud or in other galaxies such as Andromeda and so on. And you look for the passage of one of these bodies, say black holes, that passes by and modifies the light coming from that distant star by lensing it, and so making it brighter for a short amount of time as the lens passes by. So imagine this halo of objects in the galaxy. If one of them passes by, I monitor hundreds and hundreds of stars for years, and I get possible signals like this. So this is what people did in the 80s and 90s, essentially, and they got no results, except for some exception, but essentially no results. So they could write constraints of this sort. This is the mass of these objects, called machos, or massive compact halo objects in solar masses, and this is the fraction of these objects that can constitute the dark matter, 0, 6%, or 100%. You see that these surveys here, Hero, Machos, and the others, exclude essentially down to a few percent, or maybe even something of the order of 0% of these objects to constitute dark matter. Meaning that there are no objects of these masses that pass by, otherwise I should have seen the lensing constraint, the lensing effect. So that was also sort of disfavored. Actually, more generally, the dark matter in the universe cannot be a baryon or just another model, whereby baryon means, of course, neutrons, protons, and so on. And that's because, as we said already, we have cosmological probes like the CMB and the BBN that tell me how much baryon matter there is in the universe, and that is essentially 4% and no more than that, while we need instead 26%. So at this point here, we know that dark matter cannot be in the form of weird astrophysical objects made of baryonic matter of the standard model. Otherwise, we are in trouble with the strong lensing mechanism and with the formation of the nuclei in the universe, in particular helium and so on, in the BBN. Now, the loophole, which has been realized at some point, is that you can have primordial black holes. So black holes which are produced before the BBN, so they don't contradict these constraints here. They can be removed from the counting of baryons before BBN happens. And we have a mass which is either too large or too small to produce this lensing constraint here. So if these two conditions are satisfied, then black holes can be a good candidate for dark matter. So I'm not talking about the astrophysical black hole produced of ordinary matter late as stars die, but very early, just after the Big Bang, and so they are subtracted to the counting of baryonic matter.
Mark, why too large to lens?
Okay, so the idea is that if you have black holes, so why too large and why too small? Too large because if they have a very large mass, their abundance will be very suppressed, so there are few of them, and so the probability that the one passes by is low. So typically, given the sensitivity of these things and the time of exposure, you don't see them. So this is why these constraints go up at large masses. At small masses, it's because if the body is too small, then the lens effect is too small. Actually, it's even more complicated than that because you have to do some quantum optics down here. So essentially, you hit a threshold sensitivity.
Yes.
So if this is what happens, the primordial black holes can be a good dark matter candidate. So the idea has been proposed very many years ago by Hawking in the 70s, but it has been sort of forgotten for many decades until the first gravitational wave observations came out, because at that point, for reasons that we can discuss, black holes became very popular again, and the explanation of those gravitational waves from merging black holes in terms of merging primordial black holes was popular. Okay, so let's look at which masses these primordial black holes can have. So this is a sort of summary plot of the parameter space. So again, this is the mass of the primordial black holes or machos in grams or in solar masses. And this is the fraction of dark matter that they can constitute, 100% or a very small fraction. Now in log scale. So these are the microlensing constraints like before, the same masses before. And as you see, if you are lighter than that, then you have a region where these constraints are open, and you can have a value of masses which are possible for constituting the 100% of dark matter. So I'm not going to discuss the large masses because some other constraints appear, which are depicted here. And by the way, at some point we are disfavored by the very large limit, which is the one we discussed on the first day, so 10 to the 4 solar masses roughly here. But this window here of light masses is still open. So dark matter could be constituted by black holes with a mass in between 10 to the minus 16 solar masses up to 10 to the minus 11 solar masses. Two comments. The first one is you have a feeling of what these black holes are. So this is roughly the size of an asteroid. So sometimes people call it this asteroid-like primordial black holes. Not the size, but the mass. Okay, so this is the mass of a big asteroid or a big mountain, like the Everest, for instance, has around this mass here. But the size is, of course, very, very small. So we are at about 1/3 concentrated, 10 to the minus 14 solar masses, so concentrated in 10 to the minus 15 meters. That's what black holes do. And next, one comment about these bounds here. So why the window is blocked there is a lower bound to these possible masses here. So these red bounds are due to evaporation. So just one word, you probably heard that black holes evaporate, so they emit particles because of Hawking radiation. And these particles that they produce by evaporation is more important. I mean, the flux of this evaporation is more important the more the mass is small. So the smaller the mass, the larger the evaporation rate. So very light black holes, which are here, so smaller than 10 to the minus 19 solar masses, would have evaporated already in the early universe. So we don't consider them at all. Black holes with a mass around 10 to the minus 16 solar masses, so around here, are evaporating right now. So they are emitting particles by Hawking evaporation right now in, say, the galactic halo or in general in cosmology. And that means that by looking at the products of this evaporation, such as extragalactic gamma rays or electrons and positrons and so on, emitted by these possibly evaporating primordial black holes in the galactic halo, we can constrain them. So this is the lower bound. This is where the lower bounds come from. This window is at the moment untested. These bounds that I mentioned here come from a number of other suggestions, but I'm putting them dashed because they are controversial for many different reasons. So essentially, this window, at least to me, is still the only possible open window. Yeah. In the galactic halo, yeah. So that's no, of course we don't know. I mean, we can do simulations. We can do, but we'll get to that. Let's say that, as I said at some point, the global properties of dark matter are independent on what the actual candidate of dark matter is. So the halo of dark matter can be made by a huge number of small particles or a large number or a small number of huge particles, so in this case here, and their global properties are the same. The density is roughly the same, and the rotation properties, the velocity, typical velocity is roughly the same, at least compatible with the observations. Yes, yes. It's possible that we have, so if dark matter is made of primordial black holes in certain amounts, I mean, there is a flux of primordial black holes streaming towards the Earth, like there is a flux of dark matter particles, say WIMPs, impinging on xenon, for instance. Yes, that's totally possible. And actually, there are a series of funny papers where people consider what the effect would be of the impact of one primordial black hole on the surface of the Earth, say. So the effect is much more rare than WIMPs impacting on xenon, because it's the size is such that there are much fewer particles of this sort. But if it happens, the effect is actually not particularly dramatic. It's like a small earthquake, local. So it's not, there are bounds on that, but it's not particularly reliable. Okay, so the conclusion is that, conclusion for the candidates, let's say, is that all this range is possible, as I said many times. The candidates are located a bit somewhere, and in different possible models and ideas. And I discussed only a few of them, which are depicted here in these boxes. So the basic concept, as you certainly understood, is that you have to add something to the standard model, and it has to have these properties here that we have checked for all the particles that I discussed. The summary is supersymmetric dark matter, scarce singular dark matter, sub-GeV, stellar neutrinos, absent from the black holes with some sort of bottom line, personal bottom line for each one of them that I discussed. So now we change completely and we go back to the phenomenology of dark matter in terms of mostly indirect detection. So anyone, yes?
Maybe before you put the topic, I have a very nice question. You know, someone has many different candidates, and could it be that, for example, there are two candidates which exactly say of dark matter?
Yes. Yes, it could. This is typically called a multi-component dark matter. So a little bit of, say, primary black holes and a little bit of WIMPs. or a little bit of KV neutrinos and a little bit of WIMPs or whatever. Okay, so there are, my personal opinion, it's certainly possible, nothing forbids it, but is it very likely? Not really. I mean, you would have to have some production mechanism that produces similar amounts of dark matter, comparable amounts of dark matter in the universe. So you have some sort of freeze out and some sort of freeze in to produce roughly the same component, the same value, 50% and 50% or 40 and 60 and so on. So I cannot say no, but Occam razor tells you that one component is more likely.
Why again the same amount exactly?
No, in the sense that if one is completely subdominant, then okay, I mean it's 1 per mil. Yes, it exists, but basically it has no role. The important thing is what constitutes order one fraction of dark matter in the universe. Right? So what people call multi-component dark matter is to say, okay, so there are two of these candidates, each one contributing, I don't know, 20% and 80%, or 50 and 50. Okay. In that case, it's really multi-component, but I don't think it's very likely in the sense that you should have two competing mechanisms which are completely unrelated one to the other that produce it in comparable amounts. And it sounds like a bit too ad hoc. Then there is also another point. So in some of these cases, there are mutual exclusions. So there are a series of papers where people have computed that if dark matter is constituted by primordial black holes, then there cannot be also a significant population of dark matter in terms of WIMPs. Essentially because the primordial black hole would accrete dark matter, so would create an overdensity of WIMPs around itself. And these WIMPs would annihilate and create bursts of gamma rays that we should see. So that excludes the possibility that WIMPs coexist with primordial black holes and some other sort of bounds of this sort. But overall, I mean, it's just Occam razor. You say the simplest possibility is one candidate and not more than one.
Why would you need competing mechanisms? Like in the standard model, we also have like multiple families, like they are behaving kind of similar. One is heavier than the other.
Mhm.
So why could there not be one mechanism for two particle dark matter? One is heavier, therefore it's like
Okay, yes.
normal.
Yes, so you want like I don't know, thermal freeze out that produces two species of particles. Yes, but then explain to me why one of the two, the heaviest one, doesn't become the lightest one. I mean, yeah, so there are.
But exactly why do you rule this out? Why not just say, okay, there's two types? I mean, okay, the other one would have decayed into the other.
Let's say okay, it's possible. I mean, certainly there are infinite possibilities. Sort of conservatively, let's think in terms of just one and let's find that one, but it's not the only option.
But you don't need two production mechanisms, right?
You don't need necessarily two production mechanisms. You have also one production mechanism that gives you two species of particles. Yes, sounds a bit contrived to me, but you can certainly build a model that does that.
But at the end, also in the standard model, you have very many families, but the bulk of the matter is done by one.
Yeah, for instance, the mnemonic is into electrons, indeed. So let's go back to the example, yes.
So it may be, but it's not the bulk.
Okay, so let's move on and let's discuss basic facts about where is dark matter, and in particular in the galaxy. Okay, so because that's what of interest for me for the indirect detection I will discuss later. So pictorially, the situation is the following: we are in the galaxy, and we know that we are immersed in this halo of dark matter particles from rotational curves. So the cartoon is that you have these dark matter particles located in the galaxy all around, and they move in random directions. So how is the distribution? So what is the density of these particles as a function of the position in the galaxy? So we said yesterday that the first order approximation, the very rough approximation is, so the very rough deduction is that they are distributed as 1 over r squared. Remember that from rotation curves, you get something about that order there. We can do something better, more refined, by using a combination of tools, which are numerical simulations and observations, different kinds of observations. So for numerical simulation, what it means is that I do simulations on say high performing computers with a certain number of particles of dark matter, which undergo collapse and form the halo around the galaxy. And then I go and look at which distribution this dark matter has taken at the end of the process. So this motivates these profiles, which are written here, NFW, in ASTRO, and typically more, which are which have this form here. So what you do is numerical simulations. You look at what comes out from the simulation, and you draw a fitting function, which is rho density of dark matter as a function of r, the position of the in the galaxy, as a function of three parameters, which are rho s and rs, which enter in the different contribution in the different functional forms. So let's look at this plot here. This is the density of dark matter as a function of the distance of the radius. You get profiles like NFW, like in ASTRO, and like more, which are this one here, or in some cases this enhanced ASTRO, which I call the ASTRO-B. Functional forms are here, and the parameters that go into the functional forms are here. So you see that you get something which is pretty peaked at the center of the galaxy, and something which is which goes down at large distances. So two comments. The first one is that the rough, first of all, now this is done with the simulations. With simulations, you get the predictions of this sort. Instead, with observations, with essentially observations of our own galaxy or other galaxies, external galaxies, you typically get profiles which are cored, as people call them. So this truncated isothermal profile, which is this one here, or the Burger profile, which is this one here. So still as a function of the two parameters, Rs and ρs, but the shape is very different because instead of having something that is peaked and cuspy at the center, you have something that has a core at the center of the galaxy. So two comments. The first one is that the 1 over r squared is roughly reproduced in this region here. So around here, so around the location of the Earth, here, 8 kiloparsecs from the center of the sun, of the galaxy, the 1 over r squared is roughly reproduced. So we find the naive interpretation of the naive deduction of yesterday. But at the center and the periphery, the two things can be completely different, can be peaked or cored, still being compatible with the rotation curves. Okay, so the center of the galaxy doesn't affect the rotation curve in a significant way, and so it can be cored or cupped, still being consistent with the measurements of the rotation curves. And the same for the periphery of the galaxy here. Now, phenomenologically, this is very relevant because you get something which is very dense at the center of the galaxy or not so dense at the center of the galaxy. So you can immediately imagine that if you're looking for signals that come from the center of the galaxy and dark matter is distributed with an Navarro Franken white, then you have a lot of signal. If instead it's distributed with a core profile, then you have very little signal predicted, or at least a lower signal predicted. So how did I fix these values, ρs and rs? So as I said, these functions come out from numerical simulations or from observations, and these values here are fixed by essentially giving two constraints. So one constraint is to say that the local dark matter density has to be 0.4 GeV per centimeter squared, centimeter cube. So at the location of the Earth, I assume that the density is constant is the same for all the profiles, and it is this value here. And I normalize, so I need two constraints, right? Because there are two free parameters, ρs and rs, and I normalize the total mass of the Milky Way to 10 to the 12 solar masses, which is what I measure in general. So these two values are determined by stellar kinematics, so the movement of stars in the Milky Way, and are pretty reliable within, say, a factor of 2 between this value and this value as well. using these two constraints, I fix this point here and the total integral so that the profiles are all consistent. And they give me these values determined here. Okay. Okay, so that's for the distribution of dark matter. The summary is that it is unknown to a large extent, with some educated guesses that come from simulations, numerical simulations, or from observations. The benchmark points are the value of the density here at our location and the total mass of the galaxy, which is this value here. And what about the velocity distribution? Velocity distribution also comes from numerical simulations. So here you see a collection of different simulations. And roughly speaking, we can consider it to be a Maxwellian, so something which has this shape here. This is the speed distribution, the velocity distribution in kilometers per second, as the inverse of kilometers per second as a function of the speed. So the velocity distribution. So the Maxwellian is this, being the light blue line, centered around 200 kilometers per second. And the different simulations find something which is a bit different, but not so different. As you see here, this is a compilation from some years ago. So roughly, we can consider the dark matter particles in the halo moving around with a velocity distribution which is Maxwellian, centered at around 200 kilometers per second. And this is what enters in all the different searches. This comes from simulations. So someone was mentioning about the rotation of the halo. So the idea is that this halo that I have depicted here is spherical and static, while the galaxy is turning it's flat, it's a flat disk which is turning. So the assumption that the halo is spherical and static comes from structure formation. So the basic principles of structure formation, so how this collapse of dark matter particles happened, leads us to believe that the halo remains spherical, doesn't collapse to a disk, and does not rotate together with the galaxy. We could discuss that in detail, but basically it comes from how the gravitational collapse behaves during the formation of structures. Now, nothing forbids the fact that a little bit of rotation also exists, which is called the co-rotating halo. That sometimes people assume that a little bit of co-rotating halo together with the galaxy occurs. And also the shape doesn't have to be necessarily spherical. There are refinements in which the shape is a bit more flattened or a bit more oblong, and it depends a lot on the details of structure formation. The zero-order assumption is spherical and not rotating with possible complications. Okay. So next, my last half an hour, a bit less actually, is about how we search for dark matter. Wait, I will pause a second to see if there are more questions. Okay. So how we search for dark matter? The three standard techniques are direct detection. I'm not going to discuss it at all. Production and colliders, I think we have no time in the end. And instead, I will talk about indirect detection. So the basic principle of indirect detection is that we look for the products of dark matter annihilations, or possibly decays, but let's say annihilations, of dark matter particles into standard model particles, which are listed here. So photons, high energy photons, antiparticles, positrons or antiprotons, or even antideuterium, and possibly neutrinos and antineutrinos. In the astrophysical systems, which can be the galactic center, the galactic halo, or massive bodies in the case of neutrinos. So we discuss essentially antimatter here, positrons and antiprotons, and then gamma rays, and then finish. So indirect detection. Let's start with antimatter, positrons, and antiprotons. So the idea is the following, the cartoon picture is the following. So I have the galaxy, I have the dark matter particles in the galaxy, and in the galaxy, in all given point of the galaxy, the dark matter particles and antiparticles annihilate, exactly like they did in the early universe, producing fluxes, yes, being a source of standard model particles such as positons and protons, positons, electrons, protons, and antiprotons, and so on. So we'll discuss that in a minute. Now, usually I focus on antimatter, so antiprotons and positons, just because antimatter is less abundant from astrophysics. Okay, so it's useless to look at the electrons, which are very abundant in the cosmos, in the galaxy. Let's focus on positons, and the same for protons and antiprotons. The production is always symmetric, typically, but we focus on antimatter only. So I produce, say, positons everywhere in the galaxy, wherever dark matter is located, with a probability that depends on how much dark matter there is in that point. And then these particles have to propagate in the galaxy and come to the solar system where they are collected. So they will go around in the spiraling around the magnetic field of the galaxy, so losing some energy by synchrotron radiation and other things. They will be blown out by the stellar winds, convective winds produced by the stars in the galactic plane. They may suffer spallation, so collisions on the interstellar gas if they cross the galactic plane. And then at some point, hopefully, they will get close to the solar system and they will be collected by the experiments located at the location of the Earth. So you realize that there are two steps in this business. The first one is to produce the particles here in the annihilation term. And then the much more complicated and astrophysically dependent step is the propagation from the source point to the detection point here. So let's discuss first the production, so the annihilation part. This is done usually in a model-independent way. So what we do is that we say, okay, so we have dark matter particle and antiparticle. They will annihilate in some way that I don't know. I mean, depending on the model, this will be some sort of annihilation into what we call the primary channels. So we can annihilate into, say, a pair of W plus W minus or BB bar or tau plus tau minus and so on and so forth. So all the possible combination of pairs of particles in the standard model. It can be 100% into one channel or a combination of branching ratios into the different channels. Then, once I have the primary particles, that these will, since they are all unstable, they will decay and hadronize and make their parton showering until we get to the only stable particles in the standard model, which, if I'm talking in terms of charged particles for the moment, are essentially electron positrons, protons, and antiprotons, and possibly light nuclei such as deuterium and antideuterium. So this part here is standard model physics. I know how the W decays and which kind of products it produces. I know how the tau decays and which kind of products it produces. This part here is the unknown phenomenological part of the dark matter, on which I'm not saying anything. So I can write down the spectra of final products in the last step as a function of the primary channel in which they have annihilated. So let's look at one example. These are the spectra of positrons, so final state positrons, coming from the mass, from a dark matter with a mass of 1 DV, annihilating into different channels which are written here. This is their spectrum, so the number of particles, the n over the x, where x is the kinetic energy of the positron divided by the mass. So if you want, this is just the spectrum of positron, the n over the e, produced by this annihilation into the different annihilation channels. So you recognize a different spectra with different shapes here, depending on the channel in which you annihilate. For instance, let's look at a couple of examples. If I annihilate directly into electrons and positrons, I have something which is very peaked up here at a very large mass, exactly because I'm annihilating directly into plus and minus. If instead I annihilate into quarks, such as BB bar, then these BB bar quarks will hadronize and do parton showering and so on. And what you get is lower energy positrons coming from the end of the line. Okay, so BB bar produces B mesons, the B mesons produce pions, the pions produce electrons and positrons, and you have something which is a bell-shaped thing like this. And the same is true more or less for antiprotons, where you have always some sort of bell-shaped thing. Here you have no peaked cases because you always have to go through a hadronization step in order to get something, and so you typically have a bell shape like this. So let's not look too much into the details, but look at the final results. So what I'm looking at is a sort of, when I'm doing indirect detection and production, what I'm looking at is a sort of bump due to dark matter of this sort here. So the flux of some particles, let's say positrons, will be a bump on top of something which is assume the background, which is due to astrophysics and different kinds of astrophysics. And this bump carries information about the process, dark matter annihilation. So the end point of the bump will be related to the mass of dark matter, because that's the total energy disposal in the center of mass, right? So if I annihilate 1 TeV particles, annihilating against another 1 TeV particles, the maximum energy that the plus and minus can have is 1 TeV each, right? So the end point of the spectrum is the mass of the dark matter. The shape of the spectrum, the shape of the bump here will be given by the primary channel. As we have seen before, the different bumps are a little bit different depending on which primary channel I choose. And the normalization will be given by the cross-section, so how often these annihilations happen at the different points of the galaxy. So up to here, I have a sort of prediction in terms of 3 parameters, which are the mass of dark matter, which gives me the endpoint, the cross-section, which gives me the normalization, and the shape, which is given by the primary channel. But then, as I said, I have the second step. The second step is propagation. So the particles produced in each given point of the spectrum have to go around and finally, at some point, get into us. And this is the difficult part, because there are many things that happen. So I'm just flashing a few ideas. Diffusion, so the idea is that these particles diffuse as they are doing a sort of random walk, these electrons and positrons and so on, and the protons and so on. They do a sort of random walk in the granularities of the magnetic field. So they sort of going around and scatter over different bits of the magnetic field, doing some sort of so you can discuss this, you can describe this as the diffusion process of particles from the given point of production down to the point of detection. But as they do this diffusion in the magnetic field, they also lose energy by synchrotron radiation, because they are charged particles in the magnetic field, so they emit the synchrotron radiation. By Grant-Strahlung, if they hit gas particles, so matter particles. By inverse quantum scattering, if they hit photons in the environment of the galaxy, and so on. So while they proceed, they will lose some of this energy, of their energy. And then, as I said, they can suffer the convection of the winds of the stars. They can suffer the spalations when they cross the solar, the intergalactic, interstellar medium. And finally, they are also to enter into the sphere of the sun, which is meaning that they have to penetrate the magnetic field of the sun and the solar wind of particles in the sun. So this is a very complex process, which is sort of modeled in the following way. I write an equation, a diffusion loss equation, which tells me how the spectrum of positrons, say, evolves as a function of all the things that I just discussed, which are written here. Don't look at the equation itself, but just look at the fact that this is a differential equation. It is telling me how the spectrum of, say, positrons evolves in time as they travel around, as a function of all these processes here, so diffusion, the energy losses, the convective winds, the spirations, and the source, the injection, which is due to the annihilation of dark matter particles in a given point. So this equation is a differential equation, and it's solved in a volume, which is depicted here, a sort of tuna can that encapsulates the galaxy with a certain height L. So the idea is that inside this box, the magnetic fields of the galaxy are strong enough to keep the positrons or the protons contained, and so they will keep going around until hopefully some of them get to us. Outside of this box, we assume, by say, drastic assumption, that the magnetic field of the galaxy goes to zero, and so if the particle gets to the edge, then it flies away without any obstacle, and so it's lost. So we solve this differential equation inside this box here with these boundary conditions that are that at the edges, the flux goes to zero because the particles fly away. Okay. The solution of this equation will give me the spectrum at any given point of the galaxy, so in particular at the detection point, which is the location of the solar system. However, the problem is that in this equation, we have a lot of free parameters. So all these processes here will depend on a lot of free parameters. For instance, look at this diffusion coefficient. It will depend on certain current coefficient K, which is K0 times energy to the power delta. These equations, these parameters are free parameters that govern how diffusion happens. Or think, for instance, that this size of the box, this L, it's a free parameter as well. We don't know how much how high the magnetic field extends above and below the galaxy. So these parameters, L, delta, K0, and so on, are, or Vc, the velocity, the speed of the convective wind of stars, are free parameters due to related to the astrophysics. The way we fix them is to solve the same equation for ordinary cosmic rays. So for cosmic rays produced by ordinary astrophysics, so by stars located in the disk, and fitting the results of measurements of cosmic rays, of ordinary cosmic rays, gives me values for these possible parameters here. And then plug these values into the equation for dark matter originated particles, and I find the solution for the spectrum. Yeah, oh, sorry.
Yeah, a question regarding the diffusion term. It seems, well, it is all the grand equation looks complicated, but the diffusion term not too much. Shouldn't there also be a spatial dependence when it comes to some parts of your galaxy be more dense than others, or?
I didn't understand. So you're saying that diffusion coefficient is dependent on space?
Yeah, space, or is that like roughly everywhere in the state?
Okay, so that's a very good question. In first approximation, we assume the diffusion coefficient to be independent on space. And as you see here, I've taken dependence only on E, only on the energy of the particle which is diffusing. That's a very rough approximation. There are more defined treatments in which diffusion is dependent on the position, which is actually, I mean, understandable in the sense that diffusion depends on the value of the magnetic field. And so if we are very far from the center or very far from the periphery of the galaxy, the magnetic field will be different. So diffusion will be different. In first approximation, we take it as constant, but in more refined analysis, we take it as dependent to the position. The very detailed, refined treatment is considering the diffusion depending on the actual geography of the galaxy. So saying if I am in the spiral arm, then the diffusion is this and that. If I'm outside of the spiral arm, the diffusion is different. That's almost never done because it's too complex. We do some modelization. That's for the diffusion. The same thing is also true for the energy losses and for the convective wind. We just take reasonable assumptions, mostly coarse-grained, so not too much refined. Okay, so I was saying that I will fix these parameters using ordinary cosmic rays, and this is what happens. So I take different setups. I fit the results of ordinary cosmic rays, and I end up with some sets of parameters that are typically called min, med, and max, which are compatible with the results of fitting the ordinary cosmic rays. These values, these sets of parameters, are determined by ordinary cosmic rays and plugged into the previous equation for the evolution and the propagation of cosmic rays from dark matter. Look at, for instance, the typical uncertainties. L can be 1, 4, or 15 kiloparsecs. So this size of the halo can be very thin or very wide. And this will determine quite intuitively how many particles, positons, say, I get from dark matter. If L is very thin, then this tuna can is a very thin one, and so many particles will be lost at the edges, and so we get fewer positons collected in the end. If this L is very thick, then they will stay contained for much longer, and so I will get more back there. So typically, large L gives me a maximum flux, which is why this set of parameters is called maximum, and small L gives me a minimum, and so on and so forth. So all this is an industry that goes on for since decades. Using ordinary cosmic rays, I fix sets of plausible parameters. So this means that our nice picture of before gets sort of complicated by the astrophysical propagation, because I have that the dark matter abundance, so where dark matter is distributed, influences the normalization. If there are regions which are very dense of dark matter, I will get more flux, and if there are regions which are less dense, I will get fewer flux. The propagation will change the profile, the shape of the spectrum, because I said that they lose energy by many mechanisms, such as synchrotron radiation, inverse Compton, and so on. And then, so this nice shape that I had before gets sort of disrupted. And then I have to deal with the background, because I don't know actually what the astrophysical background is. Is it something like this? Is it something like this? Or is it something like this that fakes a sort of bump? And so I'm a sort of competing with the possible signal from dark matter. So that's the whole rule of the game. Let me give you a couple of examples. So if I take antiprotons, these are the final results, so the flux after propagation, the propagated flux of antiprotons, having fixed the same dark matter mass as before, with some parameters like before from astrophysics, exactly the same as before in the BV channel. And I change, so I fix a certain profile of dark matter in astro, and I change the setup of propagation parameters. You see that the typical uncertainty is of the order of 2 orders of magnitude. So propagation affects your prediction by about 2 orders of magnitude. If I fix the propagation and I change the distribution of dark matter among the profiles that I showed before, also you change, you have an uncertainty of about 1 order of magnitude. So the spectral shape is more or less conserved because antiprotons do not lose much energy, but the normalization is a lot affected by this choice or this choice. For positrons, it's similar. So you have that the spectrum is also affected by the propagation by maybe a little bit less, a factor of 10 small energies and much less at large energy. And also by the choice of the propagation, the choice of the distribution of dark matter profile, especially indeed at low energy. So the whole aim is getting these spectra here and comparing them with data and see if we do see an excess on top of the physical prediction, and if yes, infer the properties of dark matter distributed here. In the last 3 minutes, I will discuss gamma rays. 3 minutes, right? Yeah. So gamma rays from the annihilation of dark matter. So here the history is simpler. Actually, the story is simpler because we can look at more precise. I mean, we don't have this whole propagation thing. Right? So gamma rays, of course, go straight. So we just look at regions where the dark matter is densest, so typically the center of the galaxy, and we look at the production of gammas in the annihilation. So there are several ways in which the gamma rays can be produced in the annihilation. And I will select essentially two. The first one is the so-called prompt emission, and the second one is the secondary emission. Prompt emission further classifies into a continuum, a line, or some sharp features. And the secondary emission classifies into different possibilities, inverse quantum, Brent Hall, or synchrotron. I will discuss just briefly this one, and then give an idea about synchrotron. So the prompt emission, they continue. Well, it's exactly like I said before. So now I have dark matter particles annihilating into primary channels. So these primary channels do their thing, and they can also produce gamma rays. Typical example is in the primary channels, I produce pi zeros from quarks coming from here, and the pi zeros give to gamma gamma. And so I have high energy gammas coming from pi zeros which come from annihilation of dark matter. So I can do like before the spectrum, different channels for different masses, and I get typical bell-shaped stuff over a range of energy which goes from the mass of dark matter up to a fraction of it, and I have to detect such a dump on top of the astrophysics. Like before, the mass of dark matter gives me the endpoint, the primary channel gives me the shape, and the annihilation cross-section gives me the normalization. And that's it. Now I don't have to deal with propagation anymore. So the signal is cleaner. Another thing which is even cleaner is when you annihilate directly into gamma gamma. Okay, so if you annihilate directly into photons, then your spectrum is a line, the Dirac delta, right? Because it's centered on the mass of dark matter. The mass of dark matter, the energy at the center of mass in the initial state is twice the mass of dark matter, so the photons will carry each one the energy corresponding to the mass of dark matter. Yeah.
The gravitational lensing doesn't change in any way.
Yes, so the gravitational lensing a little bit will change the propagation. We will have some effect on the propagation, but if you're looking at the galaxy, not much. So inside the galaxy, lensing is not particularly important, unless for some specific objects, but the diffuse emission will not be affected by much. But otherwise, you're right that if you look at very distant sources, then you have to include it. Yeah. So one observation is that, I said many times, the dark matter does not interact with photons, right? Because dark matter is dark. So the thing is that this process can happen if it goes through a loop. So it goes through the exchange of charged particles, here I call X. So this process will typically be mediated by a loop of particles, and so the cross-section for this to happen will be suppressed. So you pay the price that the signal is very clean, it's just a monochromatic line, by the fact that the normalization is suppressed because of the fact that you have to go through a loop. Another observation is that typically when you have annihilation into gamma gamma, you can have also annihilation into gamma Z or gamma X, because in the standard model, the gamma and the Z couple in a similar way. And so you can have a line at mass of dark matter, but also a line at a lower energy due to the fact that sometimes you produce also a Z, and this photon gets a bit less of the initial energy. So usually when you look for lines in dark matter annihilation, you will get a couple of lines, a pair of lines with a small difference due to the annihilation into gamma gamma and into gamma Z. Other than that, the signal is clean because you have a dark matter mass that gives you the endpoint of actually the value of the spectrum, and the annihilation cross-section which gives you the normalization of these two. All the rest are fixed stuff. So this is the prompt emission, and let me finish with the secondary emission, which means essentially the following. As I said, in the example of synchrotron radiation, as I said, the dark matter annihilates into, say, leptons, in the example of here into electrons and positrons. So we can look at electrons and positons as the messengers, but we can also look at what electrons and positons do. What they do is that in the magnetic field, they emit synchrotron radiation by spiraling the magnetic field. And typically this ends up being in the domain of radio waves. So a secondary effect of dark matter annihilation is the production of radio waves from the electrons and positons in turn produced by dark matter. So it's a doubly indirect, right? Because you have to produce electrons and positons, and then those have to produce emission by synchrotron. So it's more complicated to compute. You have to compute the population of electrons and positons from the dark matter annihilation in the galactic center, for instance, where the dark matter is densest. And then you have to compute the power emitted into synchrotron for a given configuration of the galactic magnetic field, and so on and so forth. So this gives you a more indirect way, but possibly compelling, complementary way to test the emission, the annihilation of dark matter particles. I think I have to stop. The last part on which targets we look at, but I mean, let me just say that it can be the galactic center, the places where dark matter is dense, the galactic center, the dwarf galaxies, galaxy clusters, or other topics, places which I'm not going to do it. Okay, so I'm done. Thanks.
Well, I would suggest the following. We can have maybe 5 minutes for a few urgent questions. Then in the afternoon, at the end of the lectures, we have 1 hour of question time where all the speakers, all the lecturers are invited. We can save the first part maybe for some questions on this part. You just briefly touched in the first part, such that we can then go to the outreach event. So let's see if there is any question now. And we can keep anyway half an hour for the break. So we just take some time for the lunch break. Yeah, please.
Thank you very much, Marco, for a very nice presentation. I have a very general question, like you followed the first evidence of like the rotation of the galaxy to find the position of the dark matter in the galaxy. So my question is, the other two evidences like the cluster of galaxies and precision cosmology are in agreement with that position then?
And so you're mentioning which evidence from the galactic center? No.
Yes, actually, you were discussing about the position of the dark matter in the galaxy.
Yes.
And you, if you are like we have done it following the rotation of the galaxy mathematics, like we inversely proportional to 1/r whatever. So the other two evidences are in agreement with this, that the dark matter is located at that position, right, or not?
Yes. So I'm not sure I understand the question, but let's say what I'm saying is that the distribution of dark matter can follow each one of these profiles, and all of these profiles, density as a function of the distance from the center, is compatible with the evidence that we have, which are essentially rotation curves and structure formation in general.
Yeah,
So,
this is my question. That it is in the agreement with the other two evidences, like the clusters of the galaxies.
Okay. So yeah. So in clusters, you have other profiles. Actually, you have the same profiles but with other parameters. So we infer also from simulation of the distribution of dark matter in clusters or in other objects. And yes, so whenever we get a certain profile, we have to test whether it's compatible with the evidences from, say, the distribution in clusters. Yes, typically it is. Roughly speaking, the NFW profile is the most popular one because it's believed to be scale independent, in the sense that it works at the level of galaxies, but also at the level of dwarf galaxies, and also at the level of clusters of galaxies. So you have a distribution like NFW, with of course different parameters that applies both to small structures such as dwarf galaxies and to very big structures such as dwarf galaxy clusters. For some reason that we haven't fully understood, but say NFW is flexible enough that it taps to different scales.
Any other question? Please.
So you were showing the indirect detection through for post-quantum electrons.
Yeah.
I think towards the higher masses, there was a smaller uncertainty for positons as opposed to antineutrons.
Yeah.
But what is the major source of uncertainty? Because I would expect that if it's from the L, the height of the Shunakan,
Yeah.
would it be similar for both?
Right, so that's a very good question. So actually the difference between this and this, these are antiprotons and these are positrons, is that here the uncertainty is much smaller, while here is larger, and instead here it's more or less the same. So the difference between positrons and antiprotons is that positrons lose energy very efficiently, essentially by synchrotron radiation and by inverse quantum. So the positrons at high energy, positrons with energy typical of say 100 or 1000 GeV, have to come from nearby, because otherwise they would have lost a lot of their energy. Okay, so very high energy positrons come from very local environment around the Earth. So they are not very much affected by the propagation. Okay, immediately come to us. That's why the uncertainty is small.
So they do not reach the edges of the Shunakan.
No, exactly. So in these energies here, they are basically produced, say, a fraction of a kiloparsec around us, and so they don't see the edge, they don't see all the complications related to propagation. Those at low energy, yes, they do, because they can, they started from some energy, and when they get to us with this low energy, they have experienced a lot of propagation, and so a lot of uncertainty related to the size, the losses, and so on and so forth. That's why here the uncertainty is large.
Okay, great. So I would suggest that we stop here. We reconvene at 11:25. We start with Diana Fiorillo and the Nobel Liquids. And before going to the coffee break, we thank again. Break upstairs. Molto bene, mi è piaciuto molto.
Sì, un po' rushed alla fine, ma vabbè.
Sì,
Pensavo di avere più tempo, non so perché mi sono perso via con i modelli, forse. Vabbè.
sì, però quella parte secondo me è stata proprio molto chiara e istruttiva, non distruttiva.